Yeah, good evening, Anupama madam.
Yeah, good evening, Venkatramulu, and I think all the esteemed faculties who joined this meeting.
Before starting of the session, I would like to introduce you to our dear participants. Yeah, madam is presently working in TCS company. Yeah, before starting, I would like to present a brief report about the madam. So, madam, a seasoned IT professional with 25 years of extensive experience, including 23 years in the telecommunications industry. So, proven expertise in E2E delivery, release management, and agile scrum. Adopted leading complex IT programs in multi-vendor, multi-site environments with a strong focus on project planning, risk management, and resource optimization. A certified Scrum Master and product owner with a track record of delivering project delivery within time and cost parameters. Yeah, this is a brief profile of the madam. So today's resource person. So she will take 2 sessions. So from 6 to 9 p.m. So dear participants, please cooperate and take the inputs from the madam. Yeah, thank you one and all. Thank you, madam. You proceed.
Yeah, thanks, Venkatramulu. So I think first topic that today we are going to cover is deep learning for malware detection and classification. So we'll start with that. Okay. So hope everyone is able to see my screen, right? The presentation, everyone is able to see, right? Okay. Venkatramulu, I think you can confirm, right?
Yeah, it is visible.
Okay.
Okay.
So I think it will be easy if I do this. Okay. So I can make full screen.
Yeah.
Okay. So see, basically, we have been knowing about the new technologies, about the self-driving cars and the Google Voice Assistant, for example, which will make phone calls automatically. Okay. When we are driving, we can just ask Google to call so and so person, and they'll automatically get connected on our mobile without actually dialing their number, right? So all these are evolving technologies, we should say, basically, which are dependent on this deep learning technology. Okay, so I think you can relate, right? How a self-driving car will operate on the road. Okay, like how we visualize the road, it is the machine learning algorithm which actually takes the images of the road and all the obstacles that are coming on the road, okay, and appropriately guides the vehicle, and that's how it is able to drive, right? So basically, deep learning is the actual technology behind all these latest things we are able to use, okay. But malware is something which is a hidden thing behind all these, okay, where it is kind of a digital virus, to say, okay. So it will steal the data, and it can also lock the files, or it can break the systems. So basically, it's disrupting all these latest technologies, right? So let's in this session see how to stop this, okay. So let's go with the next agenda. Okay, what we are going to cover in today's session. So basically, we'll see what is malware detection and how we do the deep learning with the help of data, and what is the kind of data that we need for doing this deep learning, and what are the different deep learning models that are currently available, and also what is the step-by-step process for the malware detection. Okay, and also what is the future direction, and what are the challenges we'll be basically facing in this. Okay, so I hope we'll also have some Q&A at the end of the session. Okay, so that we can clarify if anything is not clear. Okay, so you can think of this as kind of a detective story where we shall first understand the crime. Okay, so that's where how the malware is going to affect us, right? And then we try to collect the clues. Okay, that's what the detective does, right? Then he uses his smartness or his talent to get to solve the case. Okay, so that's where our deep learning model will come into picture. Oh, okay, it is like a smart detective which will identify the problem and then try to solve the case. Okay, so at each point of time, I'll try to relate it so that it is easy for us to understand. Okay, so that, and also we can relate it, okay, to our day-to-day life. Okay, so moving on, how the threat landscape is evolving. Okay, so traditionally we had methods where we identified antivirus based on probably the signatures in the email. Okay, things like that. Okay, so basically we tried to compare it with some patterns. Okay, or some defined set of rules we were trying to frame, and trying to make our code or our programs follow that path. Okay, but the problem is with this approach, you can imagine like using a dictionary. Okay, so dictionary will have a set of say some thousands of words, right? So our traditional method was like referring the dictionary, and then if it finds a suitable or a word which exactly matches the dictionary, and then it will identify it as a malware, okay, or a threat. But what is happening right now is basically how this new malware is evolving is they'll just rewrite the strings. Okay, so the spelling will exactly or almost it will look same, but probably one word or just one letter will change. Okay, so that's how this word will not be identifiable with our traditional method. Okay, for example, let's take a word which is hacker. Okay, so ideally the spelling is HACKER should be written for our traditional method to identify it as a malware correctly. Okay, but if it is written as say HAK 3R something, okay, instead of E we write a 3, for example, then our program will not detect it as a malware, right? So basically, our dictionary also, we cannot update it every day with all these strange kind of spellings. Okay, so you can think of our traditional methods like that. Okay, you can compare it to a dictionary, and because we try to identify a set of signatures or set of strings which are not malware or which are known malware, for example. Okay, and we try to compare it, right, in the traditional method. But this is the problem that is happening nowadays, and with this latest AI driven technologies which are both used by the systems like automated self-driving vehicles and all. Similarly, the community, malware community is also using the same technologies. Okay, so that is basically why we are having all these new threat landscapes. Okay, so basically, I think that's where we are also struggling to identify the latest kind of threats we are seeing. Okay, so what we need to do is basically we should not use this traditional method where we just identify the words, or basically if we think again, go to our dictionary example, we should not memorize the words, or we should not just do a word to word comparison. Okay, so basically what we should probably try to see is a pattern. Okay, which will, for example, say that a word will always have letters. It will not have any digits. So things like that we should incorporate. Okay. So also there are various ways that malware is cropping up with its what to say, with its various changes. Okay, so imagine there's an image. Okay, so it's not only the words, but even images can be morphed, right? So basically, if there is an apple, for example, how do we identify it as an apple? We think that apple is round, it is red in color. Okay, so seeing the shape, we identify it as an apple. But what malware is trying to do is make a square apple, for example. Okay, or make a green apple. Okay, so our traditional method will fail to detect it as an apple, right? Because the shape is different or the color is different. Okay, so what this deep learning will tell us is, though the shape of the apple has changed, or though the color of the apple has changed, this is still an apple. Okay, so that's how evolved our machine learning should be, so that we can identify it correctly as an apple. Okay, so even though it slightly looks different, it should still be identifiable as an apple. Okay, so I hope I was able to explain this. Okay, so that's what is the new level of pattern identification, or we are looking at. Okay, with this deep learning technologies. So hope that is clear. Okay, so how we were doing traditionally, and how we are trying to do in a modern approach. Okay, so for that we are trying to utilize some features like SVM and random forest and these kind of things. Okay, so we'll just move on. So basically, like we said, automatic feature learning is the key advantage of this deep learning. Okay, so what we are trying to do in this automatic feature learning is, instead of listing the features of, let's go back to our Apple example only. Okay, so where the Apple features were listed, like probably the color is red, it is round in shape, or it has a shiny texture, like that. Okay, but what we need to do right now is, we need to add some more features. Okay, so that the neural network will identify it as an apple. Okay, so that's the next step we are going to learn. Okay, in this deep learning. So basically, how we do this? Okay, you might be immediately thinking, right, how we do this. So what we are going to do is probably try to feed it millions of data. Okay, so that's how we train our models, right? So I hope everyone here is aware of these terms which we are using, right? So that's by having multiple sets of data, millions of sets of data, which will have, say, for example, um, if we go to our Apple example, it has probably 1,000 images of different kinds of apples. Okay, or 10,000 images. So we'll try to feed all this data to our a model and then make it so knowledgeable that it identifies the image. Okay, so it identifies the apple with its characteristics, though the shape is different, though the color is different. Okay, so that's how we have to train our models. Okay, so that's the feature learning we are trying to incorporate by having the raw data streamlined. Okay, so we might do it like feed a lot of raw data, or we might do it with limited raw data, which is very much appropriate. Okay, so we can use multiple different types of methodologies here. Okay, so since this deep learning, we have these LLMs which are very fast. Okay, so it is not like a traditional system where we try to scan multiple files to feed these millions of different types of Apple images, right? So it can scan millions of files and it can automatically discover what is different in this malware, right? So that's how it differs from the normal software. Okay, so it means that it adapts very fast, and if there is even a slight mismatch, it identifies, okay, that it is a malware. Okay, so identifying is the key, right? As you can see, identifying the threat is the key here. So if we are able to identify it properly, then we can try to fix it. Okay, because the fixing comes at a later point of time, right? So identifying is the first step. So first step, we are trying to do it correctly by making our LLMs more understandable. Okay, having high feature learning, which are obviously scalable to adapts to vast and diverse data sets, as you can see, and it can handle massive volume of new malware also. Okay, so also when we talk about adaptability, it says about zero-day attacks. When we say zero-day attack, it is the attack on the first day of implementation of our LLM. Okay, so basically we train the data, we train the LLM with a lot of data, we put it to use. Okay, but on the first day, we don't predict that there will be an attack, right? Usually, okay, but even we should be able to prevent those zero-day attacks, because the in systems which are critical, right? It will be very difficult if we have an attack on a first day. Okay, because there are mission critical and time critical applications also, right? So usually in the traditional methods, it is very difficult to find these zero-day attacks, but we are trying to adapt our deep learning models to prevent the zero-day attacks also. Okay, so I think that is clear, and let's move on. Okay, so next comes how we are going to analyze the data. Okay, so there are concepts like static analysis and dynamic analysis. Okay, so where when we talk about static analysis, it is studying the content of the file first. Okay, so just go through the name of the file and what all are written in that file. For example, if there are some instructions or some headers. So because usually if it is a malware, we'll be able to detect with the static analysis also sometimes. Okay, so you can imagine like just taking a look of the book. Okay, just going through the cover page of a book, not opening the book and reading it. So that's how you can try to judge the book, right? That's what we try to do when we are buying a book also, right? We just take the first page and also we turn it back, we look at the last page, and we just try to see or judge a book by its cover, right? So you can relate this static analysis also with something like that. Okay, because we are not going to take the risk of running the file right away, but we just want to scan it. Okay. So probably we'll just look at, as I said earlier, any data that is captured in those files, or probably any images. Okay. So things like that. So how we can relate this is, say, for example, there is kind of a barcode. Okay. So when we see a barcode with a human eye, normally we think that it is correct, right? Because if it has that typical structure of lines and all, we assume that, okay, it is a barcode. Okay. But within the barcode itself, there can be a malware file. Okay. So, for example, it can be embedded into the image. Okay. So, normal barcode could have been converted by using little bit of changes in the data that is fed. Okay. And and the image itself can be a malware. Okay. So, what we are able to not detect with the human eye, our LLM should be able to detect it. Okay, so that's how we have to make our LLMs ready. Okay, so you can imagine a microscope, for example. Okay, so you take a DNA of a normal human cell and visualize it in the microscope, and also you can take the DNA of a virus and then try to visualize it. Okay. So probably as a normal human, we'll not be able to make any difference between the DNA of a normal cell and of a virus cell. But definitely a doctor can see the difference, right? He can make some distinction based on the pattern of the image on the microscope. So that's how our imaging technology in LLM is also we are trying to enhance. Okay, so that kind of intelligence we are trying to give to our deep learning models. Okay, so that they can identify the malwares. Okay, so I hope I was able to explain this. Okay, so let's move on. Okay, next comes the dynamic analysis part. Okay, so here, instead of just going through the data or content of the file, what we are trying to do is take the file and run it in a safe environment. Okay. So when we say safe environment, it is kind of a sandbox environment. Okay. Where it is not connected to our LAN network. Okay. So just probably a single computer or few set of computers, a small network which is isolated from the rest of our systems. Okay, so that if there is any virus in that, or if there is any malware in that, that can be contained in this sandbox environment itself. Okay, so that we'll at least keep our rest of the systems safe, and our environments also safe. Okay, so that's the idea of this dynamic analysis. Okay, so what we are trying to do is we are just running the file in the sandbox, and we are observing its behavior. Okay, so what all is triggered when we run the file. Okay, so what is getting loaded, what is getting opened, for example. Okay, is it trying to make any outbound connections? Okay, or is it trying to create any file, any system level activities trying to do, or any registry updates it is trying to do. Okay, so all these are symbols which will tell us that it might be a malware, right? So with this dynamic analysis, what we are trying to do is we try to run the file and then observe its behavior. Okay, and note down what all key things that this process is showing us. Okay, and probably if you see some pattern, like it is opening a file, it is trying to encrypt a file, or it is trying to delete the file. Okay, this will tell us that it is a malware, right? Because normally that is not the action, or that is not the sequence of activities that are performed. Okay, so that sequence of system calls are being different in this malware file that is getting executed. So with those kind of patterns, we should be able to identify that it is a malware. Okay, so to make our LLMs identify all these, what we have to feed to our LLMs is multiple patterns. Okay, not just this single pattern of open file, encrypt file, delete file, but multiple patterns like this, which will signify that it is a malware behavior. Okay, so we'll behavior train our deep learning model. Okay, so basically you can think of having a, for example, a CC camera in a store. Okay, so if you go to a supermarket, okay, so that's say some person who grabs some items, but probably if he gets some urgent phone call or something, he just runs out of the store without paying. Okay, so it can be an intentional or unintentional. Okay, but someone watching him in the CC cameras or the computer linked to the CC camera can immediately know that they have moved out of the store without paying, right? Because obviously he didn't follow a pattern where he has to go to the billing section, he has to pay the bill and move out of the store. Okay, so that pattern is missing, right? So, or the pattern is different in this case. So that's how we try to identify. Okay, so you can relate those actions which will identify that this person is probably stealing something from the store. Okay, so there will be some particular behavioral patterns, right? So probably they might not have any disguise like they show in the movies, right? But still we should be able to identify with help of actions. So that's exactly what we are trying to do in this dynamic analysis also. Okay, so just by having some patterns or behavioral based on behaviors, we are trying to identify the malware. Okay, so we just move on. Okay, so basically these are our deep learning architectures. Okay, convolutional neural networks and recurrent neural networks, and then the hybrid or advanced models. So I think we'll go through these in detail. Okay, because these are very important building blocks for us in building a deep learning model which will prevent the malware. Okay, so convolutional neural networks are based on images. Okay, so it will take all the image based data and based on that uh, try to identify the malware. Okay, so basically, this convolutional model is well suited for analyzing visual data, okay, like images or videos. Okay, so if we go back to our earlier microscope example, okay, so if we just zoom in on a tiny area, for example, it will give a very detailed image of the virus, right? So I think when we zoom in, probably the doctor can very easily identify the difference in the pattern, right? And he can immediately tell that it is a sign of virus. Okay, so I think that's what we are trying to do here in the convolutional neural networks also, where we try to zoom in on the tiny areas of the images and then try to identify the features. Okay, so if we don't identify the features, probably if we show some images of few animals, for example, like cat, dog, or similar animals, probably our LLM will just identify it as an animal, but not distinctly as a cat or dog. Okay, unless we feed it properly with all the specific patterns, right? So, in order to for the LLM to be trained and it should be able to identify perfectly, we should use these convolutional neural networks architecture, okay, and then train our model, okay. So basically, this as a practical use, we can see that in computer vision tests nowadays, it is all if you see, it is computer based, right? So before the eye specialist, ophthalmologist visit is there, they always check our vision with a computer, right? So basically, that's also we can say a small LLM, okay, which will use certain images generated by the computer and then give some data related to our vision, okay. So saying that whether our image needs any correction or not. So similar to that, as we said, medical imaging with microscopes, which will help us diagnose various diseases, and uh, and also it is used in self-driving cars, for example, because that's how they detect the objects, right, which are there on the road, and probably which lane the car has to turn into, or what speed the car has to move. So basically, all these things, we use CNNs, okay, and also in probably in the social networking sites and all these shopping websites, we have a lot of uh, user preferences being monitored, right? So Amazon, Flipkart, and all these marketplaces, they try to take the user preferences and they try to predict the behaviors, okay, so that they can give us options, okay. So when we just enter into Amazon, we can probably see, if we just type one item, all the related items will come up, right? Or if we have bought some item last time, images related to all those will come up. So these are all ways to predict the user behavior and then accordingly publish the information so that there will be more purchases or more growth for them also as a platform, right? So that's those are the few examples I can think of in terms of uses for these CNNs, okay. So I think we'll also just checking if we already discussed this. Okay, so this is a little bit more detail about convolutional neural networks, how we identify the visual patterns and how we detect the malwares. Okay, so basically we are using these concepts of pooling where layers of information is obtained, okay. So I think we'll better explain it with the diagram next, okay. So if you can see this image, the first image is what we are trying to feed it to the LLM, okay. So you can, as you can see, it is a zebra, right? So if we just use the traditional method, probably what it will just store it as a single image, okay. And if any deviations to this image, probably will not identify properly in the next stages, okay. So what we are trying to do in this convolutional neural network methodology is trying to feed this image as a very detailed image into the LLM, okay. So what we are trying to do is we are trying to put a kind of a kernel. If you can see, this yellow box is the kernel. Okay. So this yellow box. So this is a small part of the image we are taking. Okay. And we are just moving this kernel around this image and trying to capture multiple views. Okay. So if we just move it to another leg, probably here, it will give another image, right? So what we are trying to do is we are trying to take it multiple layers of this information. Okay. So So as I said, this kernel is you can think of like a magnifying glass. Okay, so a tiny magnifying glass, which is used to detect all these features. Okay, so you can what the the CNN does is it will move this magnifying glass around the complete image and try to capture all the edges, lines, or curves. Okay. So all the features that are present in this image. So it records all these as you can see this pooling data. Okay. So this uh, convolution plus all these are pooling data. Okay. So multiple data we are taking. Okay. And whenever it finds a unique feature, it will store it. Okay. So any line or any curve or any edge, anything which is a little bit different from the earlier image, it will immediately record it as a new sheet or as you can see, new data set here. Okay. So these small pictures, if we can visualize, it will be set of multiple small pictures, right? So that is called a feature map. Okay. So all these feature maps, what we do with this at the end of this exercise, we do kind of a pooling. Okay. And we try to form it as a big grid. Okay. So as you can see here, a big grid is formed. Okay. And only the important information is kept here, right? So wherever there is a distinct line or a distinct curve, so the distinct information is getting shared. Okay. So, so this is kind of a common type of pooling technique that we use. Okay. Where we take a small section and just keep the image stored. Okay. So this process is repeated again n number of times. Okay. Not just once, but multiple times this process is repeated. Okay. So by repeating this, we are generating multiple sets of data. Okay. So this pooling data is again, as you can see, it is increasing with each repetition. It is increasing, right? So like that, multiple iterations are done, and finally, we have these multiple layers of data. So this is the first step of this process, where we get the entire feature maps, okay, or the feature extraction. So everything from how the lines are there, or probably how the ears are defined, eyes are defined, everything is captured in this feature extraction exercise that we have done as a first step, right? Next, what we do is once we have all our feature maps ready, we take all of them and arrange it into single lines. Okay. So this you can see as a flattened line layer, right? So like this, we try to arrange all those images, and So we try to arrange all of them, and then this is fed into the connected layer. Okay. So here, as you can see, so this part of network is like our classic neural network. Okay. Where these little circles you see here, right? These are the neurons, and they are all connected with each other, as you can see, with the different lines, right? So making it as a network. So this is the classification step basically. Okay, where we are trying to classify these images that we have taken. These lot of images we have taken in the earlier stage, right? So those all we are trying to get them classified here. Okay, so finally, what we are trying to do in this last step is, as you can see in the output step, so based on all these different combinations, so you can see various permutations and combinations here, right? So these neurons are coming to. So as you can see, the probability is given as 0.7% it is zebra, and 0.2% it is a horse, and 0.1% it is a dog. Okay, so see, you might be wondering why we are feeding a zebra and it is just giving a 0.7% of as a zebra. Okay, but see, again, this is based on this classification, and we have to take the output as the maximum value as the correct output here. Okay, so if it totally adds up to 1, then it is appropriate. Okay, so it should come, the softmax activation function should come to 100%, for example. Okay, so what this determines is it is probably 70% zebra, 20% horse, and 10% dog. Okay, so but it is basically saying this based on the lines, curves, and all those which are getting identified. Okay, but it's not something to worry, because finally, I think this will help the LLM to identify different types of zebras. Okay, that's how we have to understand this. Okay, so it's like how we think also, right? For example, seeing the stripes, probably we just conclude that it is a zebra, right? Sometimes, and probably just seeing the ears of a dog, for example, we just conclude it as a dog, or we can conclude it as a dog. So that kind of reasoning which we have as a human brain, so that kind of reasoning we are trying to feed it to our LLMs also. Okay, so like it will be, I cannot say it is guesswork, but it will be more of how these images or patterns are matching in this picture. Okay, so that's how we are trying to make this make our model as near as possible to our human brain. Okay, so I think that's how the complex images are being fed, and uh, we are trying to make our LLMs with this convolutional neural network methodology. Okay, so it's not always images, right? So it will be a lot of other data also that the LLMs are have to be trained on. Okay, for example, there will be if you think of a language translation, for example. Okay, so your LLM wants to work. You want your LLM to work as a language translator. So there you don't need any images, but there will be a lot of words, lot of sentences. You need to have correct sentence framing a correct sentence, and grammatically it should be correct. So a lot of things like that will be there, right? So there you will not be using this convolutional neural network, but rather this recurrent neural network. Okay, so what a recurrent neural network does is process sequences. Okay, so it will be like a set of data which is kind of arranged. Okay, so you can just think of a sentence. Okay, So sentence has probably some set of words, right? So what we do, each word by word, we feed it to the neural network. Okay. So uh, I can explain it with an example again. Okay. So let's say the flower is beautiful. Okay. So in this sentence, we'll just feed just the first word the, okay, as a start. So the neural network, the recurrent neural network, what it does, it takes this input, stores the, okay, and generates an output. Okay. So next we give the flower is the flower. Okay, just the flower. So it has a hidden memory kind of. Okay. So in our first set, only one word was there in the hidden memory. Next we gave the flower also. So it stores first then the flower, and then it generates some output. Okay, for example. Okay. So imagine a language translator. Okay. So for example, it is converting this the flower is beautiful from English to French. So the output will be the French word. For the flower, what is the equivalent French word, for example? That will be the output. Let's just assume for now. Okay. So with this each word by word feeding, so next again the next two words will feed one by one. Okay. This is a sequential process. Okay. So recurrent neural network is always sequential, the behavior. So word by word, we will try to feed it. So what happens is the hidden memory will keep on adding up. Okay. So at the first step, it was only the, right? At the second step, it was the flower. Next, the flower is at the third step. And the last step, it is the flower is beautiful. All four words it has in the hidden memory. Okay. So what we are trying to make it is have more knowledge in this process. Okay. So see, this is not the only sentence we are going to feed it, right? Like this, we are going to feed it multiple iterations, hundreds and thousands of sentences of English language. Okay. And then make it a very strong LLM with a lot of, you can imagine the hidden data for this recurrent neural network will be so huge that it will be capable of having all the possible combinations for the English language vocabulary or sentence building. And it will have many things. Okay. So now we feed all this input data to a vector. Okay. So vector is what you can imagine as a converter, basically. Okay. So it converts these English words into French words. Okay. For example, flower will have an equivalent French word, right? So what the vector does is just replace this flower with the equivalent French word. Okay. But again, our LLM will have with this all this data that we have fed it will have so much understanding that it will appropriately grammatically correct French sentence, it will give as output. Okay. So that's how we are training our deep learning model. Okay, with this recurrent neural network. So I just took this translator as an example. Okay, but you can think of or apply this sequence methodology to many things. Okay, so we will see going forward what are the applications for this RNN. Okay, so you may tackle a variety of problems using this. Okay, speech recognition is one. So you are using Siri, right? Some of you might be using. And how Siri recognizes is basically uh, by our voice, and it will try to match the name in our phone. Okay. So though the pronunciation might be different, okay, probably let's take a name Rama. Okay. So I might say call Rama. Okay. Or I might say call Rama. Okay. So Rama is a male name and Rama is obviously a female name, right? But for Siri, it will just take both of them as RAMA and just dial the number which is fed in our contacts as RAMA. Okay. So it will not logically try to think and all. It will just map. Okay. So that's how the virtual assistants are working. So Siri, Alexa, all these. Okay. So how we are speaking the language and how they are interpreting. Okay. And appropriately they are responding. Okay. So what we have to do is, in this case, be cautious and probably to our Rama or Rama, we appropriately make some additional second names properly and give that name to Siri when we are called to call the right person. Okay. So like that, RNNs are being used in speech recognition. Okay. And machine translation. Okay. As we said, the translation languages. That's the same example we have discussed earlier, right? And also for chatbots. Okay. So chatbots are uh, you can pose a lot of problems right onto chatbots. Okay. So as you can see, um, probably they have become kind of experts in handling things day to day. Okay. So I think I'll just quote a small example of a chatbot usage which happened yesterday in my home. So I think probably after 40 minutes you will just need a small break. Okay. So what happened, my kid wanted to book movie tickets for this Friday. Okay. So he just asked the chatbot, is Friday a holiday? Okay. So probably in the pronunciation or the way he asked the question, the chatbot probably didn't understand properly, and it gave a response saying that this Friday is a holiday for Good Friday. Okay. And immediately this guy went to his father and they booked the tickets for some, I think, next immediate movie, War 2. Okay. And later, after half an hour or so, 1 hour, I came home and they were telling me, like, we have booked tickets on Friday. And I said, no, no, you guys have school, college. They were saying, no, no, we don't have because it's Good Friday. So no one in the house, my husband, my two kids, they were not even thinking that Good Friday is not in this part of the year, right? Immediately I said it's in April, normally it's not now. So they went back and they again checked. So they checked their diaries. It was not a holiday. So basically then my husband questioned, like, how did you get to know that it is a Good Friday? Then he says, I asked the chatbot and the chatbot told me. Okay. So it is just how I think the wrong interpretation, or probably this guy might have pronounced it wrongly. But I just wanted to quote a short instance which happened. Okay. So basically, that's how we are so much using things in our daily life without our actual understanding. Okay. So I was also surprised. Basically, are we using chatbots so much? Okay. So we could just go to the wall and see on the calendar, right? Whether it's a holiday or not. So next, we move on to this time series forecasting. Okay. So how RNNs are helping analyze the financial data. Okay. So how the stock market's prediction is done. So a lot of tools have come up which will help the brokerage houses in predicting the stock market movements and also weather patterns you can see. Okay. So a lot of forecasting can happen based on the changes that are happening in the oceans or probably the images, satellite images that are getting generated. So scanning all those things, we are able to predict. Okay. And also music generation. Okay. So from existing pieces of music, they are able to generate new melodies. And you can see a lot of AI developed video content also. Okay, I think in social media also we are able to see a lot of videos cropping up with the help of AI generated, right? So all these we can say are examples of RNNs. Okay, how we are trying to generate. Okay, and how we are going to utilize them in our day-to-day life. Okay, so let's move on. And Okay, so since it's a working day, a lot of calls are popping up. Okay, so next we have this long short term memory concept. Okay, so as you have understood, this RNNs require a lot of computational power, right? Because as you can see, we have fed the data step by step. Okay, so for each input step, there is some kind of execution happening in the background, right? So, for example, if we take our sentence example, each word is becoming a data point. Okay, so for each of that, it is a stepwise processing that is required. Like, right? So this input is combined with the previous hidden input, hidden state input, right? And a new hidden state is produced after every iteration, we can see, right? So as you can see, this is repeated each time. And with this repetition, we are carrying the information forward, right? So for this, lot of computational power and lot of time is also required to train our models, because it is a step-by-step process, right? So if there is, for example, a very long sequence, obviously it will be time consuming, right? So what happens during the training, right? The gradients can become very small. Okay, so I hope you understand the gradient, right? The gradient is just the small variation that we give for this LLM. Okay, so if you compare the hidden state 1 and hidden state 2, there is little bit of extra information in hidden state 2, right? So that itself we can call as a gradient. Okay, so these gradients can become very small. As you observed in our sentence example, word by word we were feeding it, right? So the gradient is very small. Okay, and see, if we want to train it quickly, probably we can try to feed it sentence by sentence also. Okay, but at that time it will be like the gradients will be higher, right? So uh, what the hidden state will store, if we just feed it sentence by sentence, is just the sentences will be stored. Okay, so I'm just trying to relate to the translator example so that you better understand and try to uh, understand the problem we'll face, right? So instead of words, the hidden state will have sentences, and during a data comparison at a later point of time, it might not be able to match those words, right? Probably it will try to match the entire sentence. And if it doesn't find the sentence, it cannot determine the output, right? It is confused. So kind of, right? So that's the reason why we have to see that the gradients are not very small or very large. Okay. So because if it is very large also, the learning will not be good. Okay. As we understood. And if it is very small also, it will be very time consuming. Okay. So basically, if there are any dependencies in between also, it is difficult to capture in case of large gradients. Okay. So and that's where the RNNs will have a limitation. So these are the limitations of the RNNs. Okay. So where there is a very small gradient or a very large gradient. Okay. So in terms of addressing that, we or rather the evolving technologies have come up with is the long short-term memory concept. Okay. So with this methodology, the model can remember even long patterns. Okay, so if you see a normal app, it might for example, it does an open file, read file, close file, like that, right? But a malware file, what it does, open file, encrypt file, and delete file. So there is a difference in the pattern, right? So that's how we can spot the difference. So this pattern is what is actually fed in our long short-term memory. Okay, so RNNs are our LSTMs are our special RNNs. Okay, that can remember all these patterns. Okay, so this is only one example I'm giving, but there might be n number of patterns that we'll be feeding to these LLMs. Okay, so basically you can think of like a song. Okay, so there will be certain notes, and there will be a kind of a tune for the song, right? So by listening to the first line of the song, you will be immediately able to predict or guess the next line of the song, right? If you have already listened the song, right? So that's how you can think of these RNNs also. Okay, so they are able to remember the pattern, remember the notes, or remember how this the information is captured. So based on that, they are able to predict. Okay, so the next we have also these gated recurrent units. So that is also another variant of RNN. Okay, so basically it is a kind of a simplified version to say. So LSTMs are capable of remembering long patterns. We can say we thought, right? So what we can say about gated recurrent units is it will be with fewer parameters. Okay, so it will not have so long patterns, but probably with fewer parameters itself, they'll be able to understand and identify long-term dependencies and then identify the malware correctly. Okay, so let's also discuss the application. Okay, so how we are applying these LSTMs. Okay, so speech recognition, as we discussed earlier, I think that is clear, and NLP, natural language processing. Okay, so it obviously helps the context and relationship between words, and also helps in accurate translation and sentiment analysis. Okay, so how to determine the emotion. Okay, based on the sentence, how emotion can be identified. So like that, and also it can summarize. Okay, long piece of information can be summarized into a short brief or precise version. Okay, so that's how also even in chatbots, so they are able to understand the user input and appropriately respond. Okay, and next we have this time series forecasting. So prediction of future values, stock prices, weather patterns, energy consumption, and all this. Okay, and handwriting recognition. Okay, so even though each of us, our handwriting is different, right? But still, the LLM is able to recognize. And financial forecasting, I think we discussed market trends and medical applications, imaging in microscopes and all that. Okay, so analyzing the medical data. Okay, so let's move on. And we have some more hybrid and advanced models also. Okay, so what these hybrids are doing is it combines the special features of the CNNs. Okay, where CNNs are capable of uh, interpreting the images, right? So with that, the sequential learning ability of RNNs is combined, and then these hybrids are able to do both. Okay, so for example, CNN extract features from a binary file, okay, which is a malware, and LSTM process the sequence of those features. So that's how we identify it as a malware. Okay, so next we have these transformers. Okay, transformers, we can again take example of a chat GPT, which are powerful sequencing. Okay, so they use attention, okay, to find important parts of the data. Okay, they have revolutionized this field of long range dependencies also by doing the parallel processing. So that's how the time consumption that is being taken in RNNs for the sequential processing, that is getting eliminated here, because these transformers are processing with high speed. Okay, so the training is quicker. Okay, so it is like they identify or they feed not all data but only key data. Okay, so it is like you don't feed word by word from every sentence into the RNN, but only based on some important words we try to identify the features and then just feed that data into these transformers. That's how we can interpret this. Okay, so that's how the speed problem or the large amount of time taking for the, training the RNNs, that can be addressed with these transformers. Okay, and auto encoders, how we can tell them is they are like compression machines. Okay, so they'll they'll fit a lot of data. Okay, so they can spot files that don't fit the normal pattern easily. Okay, they'll immediately flag it as a suspicious file. Okay, so even this training of auto encoders is relatively quicker. Okay, so that's how autoencoders are also being primarily used for this anomaly detection nowadays. Okay, so how an autoencoder functions? Okay, so basically it has a kind of an encoder and then a decoder. Okay, so basically the encoder, to say, it compresses the input data. Okay, and then the decoder attempts to reconstruct it again. Okay, from the compressed input data. So that's how the network learns to encode the important features. Okay, so this is how we are also trying to minimize the errors during the reconstruction. Okay, so so basically you can think that this entire large set of data is represented in a compact form. Okay, the input data is represented in a compact form, and then the encoding and decoding process is getting simpler. Okay, so whatever input generation, classification, and we did the reconstruction of the image at the end, right, in CNNs. So all this process is getting simpler by this. Okay, so that's how we can say this encoders are also revolutionizing this deep learning model methodologies. Okay. So basically, we can again go to our earlier example of English to French conversion. Okay, where we can think that the encoder is processing the English sentence, and the decoder is the one which will be actually finally generating the French sentence. Okay, so the in between we thought that there will be a vector, right, which will actually do the conversion. So that will leverage all these information which has been now compressed. Okay, so that's how I think we can relate this. Okay, So next, moving on. See, basically, I'm at a loss whether you are able to understand or not, but we'll try to take the Q&A section and then try to see, okay, if anything is not clear. So next, we have this deep learning pipeline, which says what are all the steps that we need to do, okay. So basically, it has 4 steps to say, right? The data collection part, where we try to collect some malware examples and also some normal examples, okay, or correct examples to say. And we do the pre-processing so that our models can understand this data. So basically, pre-processing, you can think that see, the malware data can be in some X format, right? Which might not be understandable to our model. So we want to clean the data and make it in a format that our model understands. So that's the pre-processing step. And then we feed this data to our model. And then as a last step, we try to evaluate it, how it is working. Okay. So whether the model is performing as per our standards or not. Okay. So how we can relate it is probably we give some animal pictures to kids, right? So if the pictures are blurred or if the pictures are not neat, probably they can't understand whether it's a cat or dog. They can't make out, right? So what we try to do is probably if there is some dust or something, we try to clean them up and then show to them, okay, that see, this is cat, this is dog, this is monkey, like that. We teach them, right, initially. So that's how you can relate to the model training part, okay. So data processing is cleaning the images. Collection is just taking some random animal pictures for the kids. And then after we teach them, we try to ask them that by showing the image, we ask them like, what is this? What is this? So they'll answer. So that's how we can relate it to the evaluation stage. Okay. So at the evaluation, we have to check whether the model is giving a correct response or not. Okay. So we should also define some metrics to understand the performance of our model and try to use those metrics. Okay. So that's how we can relate to this these various steps in building our deep learning model. Okay. So when we look at this data collection little bit more in detail, so from where can we get those data? Okay, because malware data we have to get, right? It is not like normal data, right? So there will be some kind of challenges happening, like this Microsoft malware classification challenge. Okay, so from there we can take the data, and we should also see, that is only one example. We should also see other areas where from where we can collect this malware data. Okay, so even probably within our companies also we'll have some kind of with the security team, they might have some malware data, right? So we have to gather as much data as possible. So the more diverse the data, that is better. Okay, because we want to train our model in all possible aspects, right? So more diversity will bring more balance to our model. So also we have to do a pre-processing step. Okay, so for example, there are various different sizes of images. We have to do kind of a resizing, and then we have to build some sequences out of the malware data that we have received. We have to formulate all of them into some sequences of system calls, okay, for example. And then we try to also normalize the data, okay. So the idea is to convert all these into a clean, uniform data set that the model can understand. Okay. So I think you are understanding the importance of this data collection and data pre-processing phase, right? Because this is the key for the LLM functionality, because it is the data that we are giving to the LLM, based on which the LLM will learn a lot of things, and we are able to train the model. Okay, so that's why this pre-processing step and this data collection step is very important. Okay, next next we have to train the model. Okay, so again, for training it, we need certain set of data, and to validate it, we'll need again few more sets of data, and we should also build some test sets. Okay, so some techniques like back propagation and optimizers are used to teach these models. Okay, so we'll not go into too much detail on them, because I think we have a time limitation also, right? So next we go to evaluation. So how many predictions were correct? So that's how we have to evaluate, right? So it might do probably 100 predictions. Out of that, probably 80 are correct. Okay, so we can say that 80 are correctly identified as malware. Okay, so probably our system has identified 100 as malware, but only out of that only 80 are really malware. Okay, so we have to see uh, probably why those other 20 which were wrongly classified as malware. Okay, so accuracy is important. Okay, how many were correct, and also precision is important. Okay, so how many of the detected ones are actually malwares? Okay, so these are like false positives that are getting generated, right? So that also have to be analyzed again, like why these additional 20 are identified as malwares, and we have to again tune our system so that this 20 number comes down to 10, and subsequently to 5, and subsequently to 0, right? So that's how we have to do the evaluation process. Okay, so it is important to find the actual number of threats, and also important to find and minimize the false positives. Okay, or false negatives also. Okay, so basically when we say false negatives, uh, probably there are 20 more. Okay, out of these 100, we said 80 only were found correctly, right? So 20 were incorrectly classified as malware, but there might be 20 more which are actually malware, but our model didn't find them. Okay, didn't identify them as malware. So those cases also we have to see. Okay, because while feeding the data, we know that how many are malwares, right? So this training data we are only feeding, and for evaluation also we are only giving the data, right? So we know how many are actually malwares, right? So based on that, we should do the comparison, and we should see that our model precision reaches 100 ultimately. Okay. So next we move on to the key challenges. Okay. So as you can see, these are adversarial attacks are one of the key challenges. So basically, adversarial attacks are attacks which are made to fool the models. Okay. So I think our next section we'll discuss in detail on that. Okay. So data scarcity. Okay, so basically this talks about we thought that we'll have large we need to have large data to train the model properly, right? But getting this large data is a real challenge to say. Okay. And also we thought that the data should be as diverse as possible, and it should be well labeled, which is very difficult. Okay. In the real world, it is not so easy to get this all these types of different data. Okay. So that is one challenge. And also models, these LLM models are mostly black boxes to people like us, because they are built with some logic which we don't know. Okay. So when we don't know the logic, we don't know on what basis the decision has been made. Okay. So if, for example, an item is classified as a malware. Okay. So if we go back to this evaluation process, which we discussed earlier, we said that 20 scenarios were actually not malware, but our LLM identified it as a malware, right? So we just know that it has identified it as a malware, but with what criteria it has identified it as a malware, on what basis it has identified, we really don't know. Okay. So that is one challenge basically for us to understand and then correct the model behavior, because most of these are LLMs are open source or even built by specified companies, but there is a lot of logic which is built within them, which is not actually available to us, right? So these uh, these black boxes is one real challenge to us. Okay. So that's what I think the interpretability talks about. Okay. So why a file is classified as a malware, or why it is not classified as a malware, we are not able to interpret from the model's behavior. Okay. Okay. So hope that is clear. Okay. And see, in a real world scenario, if we miss finding a virus, it can be a very costly affair, right? I think we all agree to that, right? Because even one small virus can entirely destroy one banking or one financial services company, and the entire transactions get halted, which will be a huge disruption for an economy, for example. Okay. So there are some new things also which are coming up. Okay. Or new ways of eliminating this. Okay. So when we are training the neural network, uh, we are trying to minimize this loss. Okay. So this loss function, it quantifies the errors between the model predictions and the actual target values. Okay. So optimizers are something our latest methodologies where this loss function is trying to be minimized. Okay. So as we said, loss function is the error that is that can be quantified between what the model has predicted and what the actual target is. Okay. So it is basically that 20 issues we can say, which our LLM could not identify. Okay. So the goal for the optimizer is now to efficiently find the set of parameters that will result in this lowest loss. Okay. So subsequently, this will improve the model's performance. Okay. So that's how we are trying to address this challenge. Okay. And next, we have a few more like this explainable AI. AI. Explainable AI is something which we, as a solution to this black box problem we discussed, right? So where we were not able to identify why our model classified it as a malware or why it didn't classify it as a malware. Okay. So we were not able to understand that. So this explainable AI is the solution for that. So this research is focused on making the deep learning models more transparent, so that people like us also can understand how this classification is happening. Okay. And graph neural networks, which studies relationship between parts of the code. Okay. So this will help us understand this complex relationship between functions in the malwares. Okay. And then this concept of reinforcement learning, where the AI model can fight back by learning defense strategies dynamically. Okay. So it is more about training our model so that it will automatically learn some new strategies by itself. Okay. So there can be a new kind of malware. Still, our model should be able to fight back that malware by learning the defense strategy proactively. Okay, without us feeding it with the data and making it learn, it should automatically try to fight back those malwares. Okay, so that's what is still in research to say. Okay. Next, next about cybersecurity. Okay, so basically, how we are using AI in cybersecurity. Okay, so think of protecting our house, um, or making it like a digital house, right? Okay, so you want to protect your house from thieves or people who want to attack you or like that. Okay, so traditionally what we were trying to have is have a guard or a watchman who will check every person who is entering into our house. Okay, so it is good way, but what will the watchman do if for example some 50 or 100 people try to barge into the house? Okay, so he'll not be able to stop and verify each person at the door, right? So, so what? How we are trying to compare it here? Our AI is it is a smart detective. Okay, so it will watch all these 50 or 100 people trying to barge into the house at the same time, and then it will with certain probably based on how they are moving forward, or based on their facial features or things like that, based on lot of cues. Okay, it will try to identify who are actually going to cause any threat. Okay, so that is how we can think that how AI is going to change the cybersecurity landscape. Okay, so I think you are able to relate, right? So think that relate our cybersecurity space to the house. Okay, so AI is like a smart detective. Okay, so AI is going to watch across all the space and probably identify the threats. Okay, and then help us address. Okay, so for example, we can still have the watchman, right? But if say at night 3 o'clock, someone tries to come and open the door. Okay, so the watchman might just check for the reason why the person is there, and probably if he thinks that it is a legitimate reason, he might just not suspect him at all, right? But what our smart AI detective will do is try to see a pattern. Okay, so if it is just a one-off instance, probably it will just keep quiet. Okay, but if it is like a daily pattern or a couple of times it happens, it will definitely identify it as a threat. Okay, so I'm just trying to give you an example, kind of. Okay, so that's how our AI is going to influence the cybersecurity space. Okay, so basically, it is going to keep an eye on various vast data sets and try to detect all these patterns and various anomalies, and then try to accurately identify the malware and appropriately block those threats. Okay, so this basically obviously enhances our defense systems, right? So next, see, we can use any technology basically for good and bad, basically, right? So basically, what we are trying to say is, for good use, we have lot of examples where we are using AI for purposes which will be useful to all of us. Okay, so well, if you have a hammer, for example, you can use it to build a house, or you can use it to break a window. So same case here with AI also. Okay, so on the good defensive side, what we can say is it acts as a digital protector for everyone. Okay, so it helps us stay safe in terms of cyber threats and protecting individuals and organizations. And basically, if you have an AI tool installed, every email that you get on your Outlook can be scanned by this AI, and it can automatically delete the email if it finds that it is suspicious. Okay, so it can spot any kind of hacking or phishing attempt, and instantly block them. So it is basically protecting our information, and it is keeping us secure, right? So on the other side, it's also AI is being used by the makers of malware, right? So even the hackers have access to most of the open source code that is available, right? So it can also be used to cause trouble, right? So earlier it was like the phishing attacks or any kind of cyber attacks were manual. Okay, so kind of initiated by a human, or human action, basically, with help of human action, triggered by a script or something like that. But now with AI, even the attacks are getting automated. Okay, so more sophisticated phishing scams and more novel ways of malware is getting developed. So you can imagine, instead of just one hacker trying to break into our computer, now we can say thousands of hackers are trying to break into our computer at the same time, right? So it can it can do with much more speed, right? And this is a real challenge. Okay, so any kind of weakness, if we have in our system, out one of these 1,000 attacks will break our computer, right? So even writing scam emails, they are so good at it. So people are actually finding it very difficult to spot. Okay. So just to quote my own example, I got one email last month on my official TCS mail ID from my immediate line manager from TCS. Okay. saying that I have done some kind of security breach. Okay. And I'm responsible for this security breach. It has been tracked and acted upon something. And if I don't give any justification, written justification, I'll be liable for any kind of disciplinary action, something like that. I got that email. Actually, being for so many years in this IT industry, I really panicked seeing that email. Okay, because at this time, sometime I was just trying to log off from my computer and I was planning to come back to home. At the time, I saw this email and I literally panicked because a cyber security event or a crime, it should be stated as like that, right? From a senior person is not taken easily by anyone, right? So it will be like an immediate disciplinary action, even leading to termination. So I immediately panicked. I was thinking of calling my manager, but I just thought, okay, let me think if I have really done anything like this. Okay, because he'll also ask the same thing, right? Like, have you done any breach? So I thought, let me think about it. And after going home, let me read it properly and then I'll speak to him tomorrow morning. I thought like that. And I forwarded that email to my another ID, which I should not have done actually. When I look back, that was a mistake. Okay, I should not have done. But I anyway did it because my TCS ID I could not access from everywhere. Like I cannot open from my mobile, and certain limitations are there because I work for a customer. So I came back home and I couldn't even actually wait till I'm back home because it's like a 1.5 or 2 hour commute back to home. So I was so tensed. In between, only on the way to home, I opened my laptop and I tried to read it thoroughly again because in that half an hour time I tried to recollect, like, did I do anything wrong? But I'm very cautious. I never do anything like that. I don't even open Google in my official laptop. Okay, so even for searching anything, I don't open. I try to use my mobile. Okay, because just to be on safer side. Okay, so I tried to read that email again, and the content is so legitimate, and at the end of the mail there is a link given where I have to give an explanation. Okay, for doing this activity. So that link, luckily I didn't click anything. But then I noticed in the email address, instead of tcs.com, it came from my manager, I said, right? Everything else was correct, but lastly instead of .com it was .co. Okay, which I initially didn't notice, but when I was reading it second time in the bus, I noticed. And immediately I called my security development lead from Hyderabad location. I had his mobile number handy, and I immediately called from my mobile. I said, this kind of email came. What should I do? And he said, okay, those emails have come up. We have been notified from others also. So just report it as a phishing email. There's just a button there. You click on that phishing button like that. He advised me. I immediately did that, and it got deleted from my mailbox also. So I'm just giving this example to tell you that even a seasoned IT professional like me was tricked. Okay, because if I'm not so conscious, I would have clicked that URL and tried to give my justification. So every matter, every word in that was so legitimate, so accurate that it was like a proper email. Okay. So, and after coming back from home also, I was still thinking while sleeping, like, how come they were able to generate such an email? Because they got to know my line manager's name also, who I do report to in TCS. They got to know his complete name without any spelling mistake. So exact email ID, everything is there in that phishing email. So we can see how intelligent, how advanced the phishing attacks have become. Okay. So how intelligent our system should be to stop or support or rather to stop these kind of attacks. Okay, so I'm just trying to tell you how it is happening. Okay, so it was one of to say very shocking experience for me in the recent times. Okay, so like we said, we can use this AI for good or bad. It's up to us. And this we all have to think how we can prevent prevent AI being used in for these malicious ways. Okay, and since both the sides have access to this powerful tool, right? How do we actually win? Okay, in this race. Okay, because both are powerful, you can say, right? Both have all access to all the latest technologies. So how can we prevent this AI from becoming a bad AI? Okay, so this all our cybersecurity professionals are working, and it's also important for us to understand and learn about this, and so that we all also can be part of this solution. Okay, and coming to this bias and fairness, see, you can imagine like a student, he's learning few things from the teacher, right? So now we can say our data is the teacher. Okay, and say for example, the teacher has some unfair ideas. Okay, so we can say a, a teacher is more for example biased towards a particular race or particular religion, for example. He might teach the same things to the or same ideas to his students, right? So see, I'm not saying this is normal practice, but it can happen, right? So in case of AI also, based on the data that we feed, there might be unfair bias that happens. Okay, so there might be unfair ideas that are fed to the AI. So this is called the algorithmic bias, where AI models are normally trained on historical data, right? So the historical data can contain human bias. Okay, and ultimately the AI also can take these biased ideas. Okay, so if we take this example of training data for specific demographics or regions, if we train AI on cyber attacks, AI might feel that it is recognizing attacks on only these demographics. Okay, and if actually the cyber attacks happen on a different demographic region, AI might fail to detect it. Okay, see, it is up to see, AI is interpreting the data in a certain way, right? So some way we can try to manipulate how AI is interpreting, but not every time, right? So what in this case AI might do is AI might only safeguard those demographic regions where we have given the data, and other demographic regions AI might think that they are not prone to any cyber attacks, and it might not monitor, is what we are trying to say. So this can lead to a discriminatory measure, right? Where leaving certain groups into vulnerable space, right? So that way AI will not be so good at protecting people in say, if we have given the training data only for urban areas, for example, AI will think that these cyber attacks will happen only in urban areas. Okay, and the rural areas will not be monitored. Okay, so indirectly we have taught the AI that attacks will not happen in rural areas. So that might not be our intention, but with the data we have taught AI like that. Okay, so those kind of biases we need to be aware of. Okay, so how in while training the AI we should be cautious and try to overcome these kind of biases. Okay, so because it's not just a mistake, right? It's very unfair, and it's it might cause a lot of what to say what bigger problems, okay? Because there might be some banking or any kind of a real-time application that got attacked by the cyber malwares, right? So basically, these kind of biases and algorithmic biases, we have to be very cautious, and we have to try and avoid them. Okay, so I think we are almost closing this and coming to the end. So I'll just try to sum up what we have actually learned in this. So as you can see, malware is evolving very fast, and we have to be very up to date in automatically enhancing our LLMs and making them making them to uh, be what to say proactively identify issues and proactively build defense mechanisms. Okay, so that's the stage where we have to be, and I agree, and we all know that it's not a perfect scenario at this moment. But I think in future, with all those researches and all we saw, right? So I think that we'll be in a much better place, and I think we can finally rely on AI fully. Okay, but we still have to see. Okay, so I think that was from my side, and probably we can have a quick 5 minutes for questions if anyone has.